All right, as promised, here are the last three problems on page 9, and we are talking about factoring. Okay, so there might become a time, right, when you are working through the factoring problems and you get stuck, right? There's nothing else that you could do, right? You could give up, but now that we are getting more into trig, we are learning more of the Pythagorean identities, the double angles, and so forth. Okay, so examples 12 and 13, we are definitely going to go ahead and implement our trig. Okay, so let's go ahead and start with example 12. It says give solutions in the interval of 0 to 2 pi. And then we have sine of 2 theta is equal to cosine of 2 theta. So my first initial thought is I need to go ahead and make everything equal to 0. So I get sine of 2 theta minus cosine of theta, and that equals to 0, right? From this point, I have no clue what to do next, right? I'm not sure if this is factorable to begin with. So I'm going to go ahead and look at my two terms, right? I have sine of 2 theta and cosine of theta. Sine of 2 theta. This looks very, very familiar with something that we learned earlier in chapter 9, right? This is our double angle formula. Right? I know sine of 2 theta is 2 sine of theta times cosine of theta, and then I'm going to continue on with the rest. Cool. So from here, right, now I have enough where I can go ahead and start factoring. It looks like in both of these terms there's a cosine of theta, so I'm going to go and factor out a cosine of theta. So I get 2 sine theta minus 1 is equal to 0. Then I can split up into 2. I have cosine of theta is equal to 0. Then I have 2 sine of theta minus 1 is equal to 0. Right? The cosine theta is equal to 0. This is just your basic. If I'm looking at my unit circle, these are those two values. We're in terms of radians, so I have theta is equal to a pi over 2 and a 3 pi over 2. Since the problem doesn't say give all solutions, it's just saying give solutions in the restricted interval of 0 to 2 pi. This is my answer. Okay. Now looking at the 2 sine theta minus 1 is equal to 0, right? I can keep going with this guy. This just boils to sine of theta is equal to a positive 1/2, right? I would go and add the 1 on both sides and then divide both sides by 2. So from here, I have sine of theta is equal to 1/2. So I'm looking at the positive values of sine. The angle measurements that have a sine of 1/2 in terms of our radians, this should be a pi over 6 and a 5 pi over 6. And there are my two solutions for that one. Okay, so now we are looking at more specifically our trig functions and what we could do with them given our identities and our potentially, right, your double angle formulas. All right, let's go ahead and do number 13. So it says give solutions in the interval of 0 to 2 pi. Right off the bat, I have 2 cosine squared of x minus sine of x is equal to a minus 1, is equal to 0, right? I have 2 different functions, right? So that means I have to get rid of one. I'm going to go ahead and focus on the cosine squared of x. Cosine squared of x, this goes back to chapter 7. This is a sneaky little Pythagorean identity, right? We know that cosine squared of x is equal to 1 minus sine squared of x. So that's what I'm going to go and plug in. I have 2 times in parentheses. I'm replacing cosine squared of x with 1 minus sine squared of x. And I'm going to continue on with the minus sine of x minus 1 is equal to 0. All right, from here, I'm going to go and distribute the 2. So I get 2 minus 2 sine squared of x minus sine of x minus 1 is equal to 0. Right, I can combine the 2 and the minus 1. So then we get negative 2 sine squared of x minus sine of x plus 1 is equal to 0. I hate negatives, so I am going to go ahead and take out a negative. I'm going to multiply the whole entire thing by negative 1. This is just a trick to help us stay more positive. So I get 2 sine squared of x plus sine of x minus 1 is equal to 0. And then from here, this is factorable, right? This goes back to when the coefficient is not equal to 1, right? You have to go and multiply the first and the last term. So as I'm working through this one, I'm going to add to a positive 1. I'm multiplying to a negative 2. So then my two factors are going to be 2 and negative 1. So if I rewrite this one, I have 2 sine squared of x plus 2 sine of x minus 1 sine of x minus 1 is equal to 0. Right, and then I can go and start factoring. I am left with a 2 sine of x plus 1. Then I'm going to factor out a negative 1. I'm left with sine of x plus 1. And then I can group that together. I get 2 sine of x minus 1 sine of x plus 1, all equal to 0. All right, here I have my two binomials, right? I can go ahead and equal both of them to 0. So I have 2 sine of x minus 1 is equal to 0. Sine of x plus 1 equals 0. This one would go ahead and boil down to sine of x is equal to a positive 1/2. Then I get sine of x is equal to a negative 1. Okay, so I'm going to go ahead and make some more space. I'm going to make this guy tinier. No, come on. Oh my goodness gracious. Okay. So here we go. Okay, again, you're just going back to the basic, right? I'm looking at the positive values of sine, where the angle measurement has a sine of 1/2. This looks like theta is equal to a pi over 6 and a 5 pi over 6. Right? It's just telling us to give solutions in the restricted interval of 0 to 2 pi. So those are my two answers for that one. And then I have a sine of x is equal to negative 1. This is the only one solution down there. I got x is equal to a 3 pi over 2. Done. Cool. All right, the last one. The last one, we have example number 14. All right, it says give solutions in the interval of 0 to 2 pi. And we get our cofunctions, right? We have 2 cotangent squared of x minus cosecant squared x minus 1. So my first step, and this goes all the way back to when we were proving Pythagorean identities, right? The first step always was to go ahead and change everything to sines and cosines. So I'm going to do that. I'm going to go ahead and change to sine, cosine. So this becomes 2 cotangent is a cosine squared of x over sine squared of x plus cosecant 1 minus sine squared of x minus 2 is equal to 0. Cool, and we see that we have this common denominator of sine squared of x. So I'm going to go ahead and multiply by the overall common denominator. Wowza. This is basically like when we did the proving trig identities into now solving trig equations. Both worlds colliding. Okay, overall common denominator, that is the sine squared of x. Right, so I'm going to multiply everything but sine squared of x. If I did that, then these two would cancel out. So then I would be left with a 2 cosine squared of x. If I did that with the second term, these two would cancel out. I'm just left with plus 1. And then this one, I am just straight up multiplying the negative 2 times sine squared of x because there is a denominator of 1 is equal to 0. Okay, so this looks a little bit nicer. couple things with this one. I'm gonna change everything to sines. So very similar to example 13, where I used this guy, right? Cosine squared of x is equal to 1 minus sine squared of x. That's what I'm gonna go and plug in from here. So I'm gonna say 2 times the quantity of 1 minus sine squared of x. And then I have the plus 1 minus 2 sine squared of x all equal to 0. And again, this right here, that is Pythagorean identity. All right, I can go ahead and distribute the 2. I get 2 minus 2 sine squared of x plus 1 minus 2 sine squared of x is equal to 0. Right, I'm just combining my like terms. I can combine 2 plus 1. That gives me a positive 3. Then negative 2 sine squared of x minus 2 sine of x, right? This gives me a negative 4 sine squared of x is all equal to 0. All right, this is going back to the basic. I'm going to go ahead and move some things around. I'm going to move this 3 to the other side. I get negative 4 sine squared of x is equal to negative 3. Divide both sides by negative 4. Sine squared of x is equal to 3/4. And I'm going to go and make things a little bit smaller. All right, here I am. All right, I'm going to take the square root of both sides. I get sine of x is equal to plus or minus radical 3 over 2. Right? This is really radical 3 over radical 4. That radical 4 just reduces to that 2. All right, then here, again, I'm just going back to the basic. I'm going to go ahead and look at the positive values of sine. In this case, where the angle has a sine of radical 3 over 2. So my positive is going to be x is equal to, what's that, pi over 3 and 2 pi over 3. And then for my negatives, those are the other two reference angles of a 4 pi over 3 and a 5 pi over 3. And this is your solution. Cool. So we see in factoring, this is when it gets a little bit messy where, yes, we are going to have to really refer back to chapter 7 and a little bit of chapter 8, given example number 12 with this double angle formula. Okay? All right.